Okay, hello everybody. Before we get started with the 1.9 video notes, let's do two warm-ups. So I want you to factor and find the x's for these two functions. So feel free to write this down, then pause the video, and then come back and I'll cover this example. Okay, so let's go over this. So first, we know that the AC, we use the X method, as you know, is my favorite. So 25 times 6 is 150. The B is 25. And now let's find the factors of 150 that could give us 25. So we got 1 times 150, 2 times 75, 3 times 50, 5 times 30, and 10 times 15. And it looks like 10 times 15 multiplied will give us 150. And when added will give us 25. So positive 10 and positive 15. Okay, so we got 25x, and now we have the replacement for 25x is 10x plus 15x plus 6. Okay, so now let's find the GCF of the inside and the first two and second two terms. So we'll find the GCF of these two and these two. So the GCF of these two is 5x. 5x times 5x will give us 25x squared. And 5x times 2 will give us 10x. Okay, and the common factor for these two is 3. So positive 3 here. And 3 times 5x will give us 15x. And 3 times positive 2 will give us 6. We bring these to the front. That gives us 5x. And we do have like terms here, which we need. And so we can carry on. So we got 5x plus 3 and 5x plus 2. Okay, let's finish this. So now we're just going to solve for the x's. 5x plus 3 and 5x plus 2. Subtract 3, subtract 3. So I got 5x is equal to negative 3. Divide that by 5. Divide by 5. X is equal to negative 3 over 5. Okay, we'll do the same thing over here for the other x. So I got 5x is equal to negative 2. Divide by 5, both sides. X is equal to negative 2 over 5. And those are our two x's. And here's a good look at the whole problem. Okay, so let's do one more. So go ahead and write this problem down and then pause it and I'll cover it for you. Okay, hopefully you looked over the example for how to factor a third degree polynomial, but let's go over it. So first we break up the first and second term. So we have x to the third plus 4x squared minus 18x minus 9. So now we have those two quantities. And let's factor out the common denominator for the first quantity. So I got 4x squared. 4x squared goes into that once. And 4x squared times 2x will give us 8x to the third plus 1. And let's factor a negative 9 out of this. So negative 9 times 2x will give us negative 18x. And negative 9 times 1 will give us negative 9. Okay, so now we have our two quantities. Let's bring the 4x out front. And these two quantities match up again, which is what we needed. I got 2x plus 1. And we need those two quantities to match up. So now we have 4x squared minus 9 times the quantity 2x plus 1. 4x plus 9, 4x squared minus 9 should look familiar to you. 4x squared minus 9 is the difference of squares. 2 squared and 3 squared. So that would give us 2x plus 3 and 2x minus 3, which gives us 4x, sorry about that, 4x minus 9. And I still have my quantity of 2x, all that times 2x plus 1. So let's make these equal to 0. 2x plus 3 is equal to 0. 2x minus 3 is equal to 0. And 2x plus 1 is equal to 0. Subtract 3 from both sides. So now I have 2x is equal to negative 3. Divide that by 2. Divide that by 2. X is equal to negative 3 halves. Okay, so let's do the same thing here. Add 3 to both sides, which gives me 2x is equal to 3. Divide that by 2. Divide that by 2. X is equal to 3 halves, positive 3 halves. And now let's subtract 1 from each side. Now we have 2x is equal to negative 1. Divide this by 2, both sides by 2, and I got negative 1 halves. And those are all my x's. All right, now that we've done the warm-up, let's go over the notes. So today what we're working on is rational functions and the vertical asymptotes. It's a little bit different than what we've been doing the last couple of days, but it's almost the same procedure. So let's take a look at this first one. We're going to find the zeros of the following rational functions. And we've been doing this for a couple of days now, so let's write out this quantity and let's solve for it. So x squared plus 2x is going to factor out the x. We see the common factor here, so let's factor out that x. X times x is x squared plus 2 gives us 2x. And now let's use the x method down here. So AC, a times c is 1 times negative 5. So we have negative 5 AC. This is multiply, this is add. And let's find the factors of 5. It's just 1 and 5. So 1 and 5, I need a negative 5. 1 plus negative 5 is negative 4. So that gives us x minus 5 and x plus 1. And don't forget, no real zeros come from the denominator. So we know that only the real zeros come from the numerator. So the first x we have for the numerator is this x. So we know that x is equal to 0. And then we have x plus 2. X plus 2 is equal to 0. Subtract 2 from both sides. And now we know x is equal to negative 2. So our two real zeros for this one are 0 and negative 2. All right. Let's go ahead and try this one. I'll try to slow it down a little bit so you don't have to pause the video. And let's use the AC method to solve for these two x's. So a times c is 1 times negative 6. So we got negative 6. The b term is negative 1. So let's go back to 6. We got 1 and 6 and 2 times 3. So 2 times 3 is 6. 2 times negative 3 is 6. And 2 minus 3 is negative 1. So we have our two quantities now. X is equal to negative 3, or x minus 3, and x plus 2. And let's bring this x plus 2 in the denominator. And we know that these are common. So x plus 2 is a whole. And then we have, let's solve for the whole. So we have x plus 2 is equal to 0, minus 2, minus 2. So x is equal to minus 2 as a whole. And then let's solve for this quantity, x minus 3. X minus 3 is equal to 0. Let's add 3 to both sides. And x is equal to 3, which gives us our other real zero, or our only real zero. Okay, there's a look at the whole problem. And here's a look at the other problem. I don't know if I zoomed out for that. All right, so here's a reminder for you. A reminder that the real zeros of a rational function correspond to the real zeros of the numerator for the values in the function's domain. So remember, if we have a whole or if we find an asymptote, those will not be in the domain. They kind of break the function at that point. So I thought we should start with what is an asymptote of a function. So an asymptote is a line that the graph of a function approaches as either x or y go to positive or negative infinity. There are three types of asymptote. A vertical asymptote, as you know, is going to go up and down. So that's a vertical asymptote. A horizontal asymptote will go sideways. And an oblique. We saw this last week where it will seem to go across both the x and y. Okay. So we'll go over this, finding asymptote and rational functions. We'll go over this in class. I'll cover that in class. Let's take a look at the previous example using the Desmos activity. Using the Desmos activity, you're going to come up with this graph. And again, we'll do that in class. So if you want to, feel free to graph it. You can graph this using Desmos, and then you'll see, we'll cover this, but we'll look at the end behavior. So I want to remind you how we find end behavior. So we find end behavior by dividing by the greatest exponent in the denominator. And for the greatest exponent we have is x squared. So let's divide everything by x squared. And now we're trying to find a constant. So x divided by 2, x squared divided by x squared. That gives us 1. 2x divided by x squared. This x cancels this x, and we end up with 2 over x, which is not a constant, so that's a 0. X squared divided by x squared, that's 1. 4x divided by x squared, this x cancels this x, and we end up with negative 4 over x, so we have a 0. And negative 5 divided by x squared is also not a constant, and that's going to give us another 0. So what we end up with is 1 over 1, which tells us that we have a horizontal asymptote at 1. And you can see the horizontal asymptote here at 1. And again, we'll go over this in class. Okay. Let's go over a couple more examples. So how do we find our zeros? Well, first we have to factor the numerator and denominator. All right, so using the x method again, x times negative, or 1 times negative 35 is negative 35. I have a b of positive 2. And let's find the factors of 35. So we got 1 and 35. 1 times 35 is 35. 5 times 7 is 35. And those are the numbers that we need. So negative 5 plus 7 gives us positive 2. Negative 5 times 7 gives us negative 35, which is what we need. So let's plug that in. Negative x minus 5 and x plus 7. Now let's factor out the second function. And 1 times negative 10 gives us negative 10. Again, this is AC and this is B, and our B term is negative 3. So 10, 1 times 10 will give us 10. 2 times 5 will give us 10. And 2 and 5 is what we need. A negative 5 times 2 gives us negative 10. Negative 5 plus 2 gives us negative 3. We got x minus 5 and x plus 2. Okay, so we got a common factor here, which is going to give us a whole. X x minus 5. Let's add 5 to both sides. So x is equal to 5 is a whole. And the 0 in the denominator. The 0 in the denominator, let's find that. We have x plus 2, because it's not a common factor. So x plus 2 is equal to 0. Subtract 2, x is equal to negative 2. This is a vertical asymptote. So we know that's a limit, because that can't equal 0. If that equals 0, then we're going to break the equation. So here we have x plus 7 over, this is what we end up with, x plus 2. We have a multiplicity of 1 because these multiply by 1. And we'll get to that in a little bit, but you'll see when that comes into play in the next problem. So let's solve for this x. So x is equal to negative 7, and that's a real 0 because it came from the numerator. So x is equal to negative 7 is a real 0. So let's take a look at this. We can see our real 0 pops up right here. We can see our whole that we found, x is equal to 5, is here. Where x is equal to 5. And the vertical asymptote that we found at negative 2 is right here. This is our vertical asymptote. This is what we're looking for. All right, let's do the next example. Next example, you should be pausing it. You should have paused it on the last one so that you can solve for those x's. So hopefully you just pause it and solve for this on your own. So let's pause this while you start working on that. All right. We use the AC method or the box method. A times C is 2, our B term is 3, and 1 times 2 is 2, 1 plus 2 is 3. So we have x plus 2 and x plus 1. Now let's do the second quantity. A times C is 1, and our B term is 2, so 1 times 1 is 1. 1 plus 1 is 2. Oh, but first, we should have factored an x out here. So we have an x. We still end up with the same. So after we factor that x out, we end up with x squared plus 2x plus 1. So x squared plus 2x plus 1. Now we did our AC method for that, or x method. So we have x times x plus 1 from here. And then we have x plus 1 again. And x plus 2 times x plus 1. Okay, so we have something different going on here, because now we have this whole term that has a multiplicity of 2 in the denominator. Because x plus 1, we can see it's twice in the denominator. So it does have a multiplicity of 2, and that's going to come into play in a little bit. But they are still limits. We can't have those equal to 0. So let's solve for that. X plus 1 is equal to 0. Subtract 1 from each side, and now we know we have a vertical asymptote at -1. So it doesn't matter which one. So we have one vertical asymptote at -1, and we also have this vertical asymptote at 0. So we have two vertical asymptotes, one at -1, one at 0. And I know what some of you are thinking, that this is a hole. And we'll talk about that in a minute. So first, is that a hole? What do you think? This one is not going to be a hole. So I'm asking you if x is equal to -1 is a hole, and let me show you why it's not a hole. We already said that it has a multiplicity of 2 in the denominator. So what does that mean exactly? It means that even after we reduce them, meaning we took the common factor, we reduced it, we still end up with 1x plus 1, one quantity of x plus 1, which would give us x plus 2 over x times the quantity x plus 1. And because the multiplicity is 2, then x plus 1 is not a whole, because this still exists. And it's not a whole, it's a limit. So because it would cancel out the horizontal asymptote that we found at x plus 1, it's not a whole. So let's take a look. I forgot to solve for this x plus 2. This x plus 2. So minus 2 here. X is equal to -2. That's a real 0. So let's take a look what this all looks like. You can see how it didn't cancel it out either. So we have the vertical asymptote that we solved for here. And we can see that right here. This vertical asymptote at -1. The other vertical asymptote at 0. We have the real 0 that we found in the numerator at -2, which is right here. And we can also see that x plus 1, this -1, is still here at the asymptote. There's no holes. So we talked about multiplicity last week. We didn't quite explain, or she didn't explain where that came from, but now you can see that if we have a multiplicity, meaning we have more than one of those quantities, then we do have to count them to see if they're going to cancel out or if there's going to be one left over so that it becomes an asymptote. Okay, let's go over this third example. Let me zoom out so you can get a whole picture of this one. So there's a whole picture of that problem. Second example. And here's a good picture of the first one. Just ignore this here. Okay. Okay, so let's talk about the end behavior, because we talked about the other day and or last week. And last week we had this term pop up on our quiz, and I didn't quite explain it. So let's take some time to explain it today. So as we read this, you can read it like this. So the limit, and we have this right here, the limit as x approaches -2, this is x approaches -2 of the function. And when we see this negative here, it describes where we're coming from. So as x approaches -2 from -infinity, meaning it's coming from the left. So this one's coming to approach -2 from the left. And you'll see it described as that. So I wrote this here so you can remember it. We see from the left here and from the right if it's positive. And we see both of those being used up here. So let's take a look at these without looking at the graph. So the limit as x approaches -2 from the left or from -infinity, the function of, or x approaches negative infinity. And you can see that here. As x is coming from negative infinity and it starts to approach this asymptote at -2, x just keeps getting more negative. Or it goes off, I'm sorry, not x, the y's keep getting more negative. So in behavior, it approaches negative infinity. And here we are here. So the limit as x approaches -2 from positive infinity, our y's get more positive, right? So it goes off into positive infinity. Sorry, goes to infinity as x approaches -2. So let me fix this over here, -2. As x approaches -2, it goes to negative infinity. So zoom out so you can see that. Okay, now's a good time to take a break if you're getting tired of my voice or if you just want to go take a little break. All right, welcome back. So let's take a look at this. Let's find the vertical asymptotes of the given rational function. Then determine the limit as x approaches -3 from the negative infinity and as x approaches -3 from positive infinity. And let's talk about the multiplicity if we have it. So let's factor this out, x minus 8, there's nothing to factor there. But we do have x squared minus 5x minus 24. 1 times -24 is -24. Our b term is -5. Let's find the factors of 24. 1 times 24, 2 times 12, 3 times 8, and 4 times 6. All right, so 3 times 8 looks like what we can use here. So we got +3 times -8 gives us -24. +3 plus -8 gives us -5. All right, so we got x plus 3 and x minus 8. You should know by now that these are common, so they cancel each other out, which leaves us with x plus 3 denominator. So let's solve for that. So we know that x at -3 is a vertical asymptote. And since they had x minus 8, the two quantities were common. X minus 8 was common. Let's solve for x minus 8 is equal to 0. Add 8 to both sides. And now we know, because multiplicity is still 1, that we have a whole at 8. So let's take a look at this, what this looks like. We know we solved that we solve for the vertical asymptote, which is at -3. So we have vertical asymptote at -3, and we can see that here. And as the limit from the left, because it's coming from -infinity, as the limit as x approaches -3 from the left coming this way, our y's go off into -infinity. So they keep coming down here and they keep going. Now the limit as x approaches -3 from the right, which is here, the function goes off into positive infinity. Okay, so let's get rid of this. We don't need that. All right, so let me zoom out so you can see the whole problem. We have our hole and we have our vertical asymptote. All right, so what are the takeaways? All right, so you're done hearing me, almost done hearing me yap here. What should we take away? First, finding vertical asymptotes on a rational function requires examining the real zeros unique to the denominator. Again, so we're trying to find these zeros down here so that we can find the asymptotes, right? Regardless of what's up here. And the end behavior of the output values of a rational function near a vertical asymptote either increase or decrease without bound. So they're either going to go more negative or go more positive without bound, meaning there's no end. They'll just continue off. All right. Hopefully that wasn't too painful for you. And maybe I'll try to spice it up in the next video.